at the very beginning, I made the bold claim that every vertex algebra somehow comes from an affine vertex algebra. And now I partially have to at least justify that. So now, today I will talk about W algebras. I will first give their definition and then tell you that there are two very different VOA constructions, and I'll state that they give the W algebras again. And then, depending on time, but I prepared quite a few pages on applications to geometry, topology, and physics. All the three things are the same thing in the setting. It's called AGT correspondence broadly, Aldai, Gayotto, Tashikawa, and we will come to that hopefully this afternoon. Did any one of you take a quantum field theory course? Or read a book? You and you? Very good. So one important thing is to have a quantum field theory that doesn't have any non-physical states, right? States of negative mass. So what do you do in order to get rid of those? Do you remember? Negative mass. So you somehow have to divide out by those, and there's a path integral procedure called Fateh-Popov ghost fixing procedure. And path integral is, of course, not totally pleasant for a mathematician, but it turns out there's another procedure named after four physicists, B, R, S, and T. I forgot what they stand for, and that's a cohomology. So that means it's instead of taking the complete space of states of the quantum field theory, you only take cohomology classes. So you have certain fermionic operators, often called ghosts, and we will identify this ghost with free fermions or pairs of free fermions. Free fermion super VOA we had. So I will now call a pair of two free fermions, psi1 and psi2, not psi1 and psi2, but ghost B and ghost C. Just that's the procedure. And then one wants to do a procedure that is very similar to this BRST formalism. So we want to somehow get rid of something, and here we don't really want to call this unphysical states, but what we think about it is we have a Lie algebra, and we choose a positive portion of it. So the way you should think about it, you draw your n by n matrix, GLN, and you choose an upper block on an upper block somehow that is nilpotent. And then you want to fix a character on this nilpotent subalgebra, and you want to do a gauge fixing that replaces your affine vertex algebra by a vertex algebra where the fields in this block are somehow forced to act by this character. And now you have to find a way to implement it. And how do you do it? This means we will now introduce some cohomology. So to give maybe an example before we completely start, an example of what we will do is the best example is, of course, SL2. So then what can we do is we write down our 2 by 2 matrix. We look at this 1 by 1 block here in the upper right corner. It's the subalgebra generated by E, not very complicated. And now we would like to do a procedure that somehow fixes E to act by the constant 1, for example. And what one does is one introduces a pair of ghosts, a pair of free fermions called B and C. So these are fermionic fields whose OPE is this one. They have a first order pole. And in particular, every mode of B and every mode of C squares to 0. So in particular, if we take the field D to be the field B of Z times the field E of Z minus 1, then then you can check that this field has a trivial OPE with itself, because E has trivial OPE with itself. 1 is just 1 that has trivial OPE with everything, and B has everything has trivial OPE here. So this means it's no problem at all to check that there are this OPE is regular. There are no singular terms at z equals w, and that is equivalent to the, I mean, it's not equivalent, it implies the statement that the anti-commutator of the zero mode is 0. So what you can do is you can define a complex pair of goals. So this is what we would maybe call our complex associated to the Lie algebra SL2, the level K, and the nilpotent element. And now one has the convention that one doesn't denote it by E, but by F, the opposite one, that you should just take as a convention. It is so, and now on this complex we have a differential, and so it turns out one can show that that the homology of such a complex is again a VOA. A VOA. It is called the W algebra at level K of SL2 corresponding to the nilpotent element F. And this is and it turns out this W algebra is the very same thing as, does anybody of you know that? What is the W algebra of SL2? Anybody already heard that? The Virasoro, absolutely. It's the Virasoro algebra at central charge 13 minus 6 divided by k plus 2 minus 6 times k plus 2. So here this just denotes the central charge. Okay, and it is a one complete Baud spectral sequence. No, actually half a Baud spectral sequence computation to verify this statement. I have it on my notes, so if you want to do that later, we can do that. But what we want to do now is we want to generalize this. Right? So this means I want to write, what I want to do is I want to replace SL2 by a Lie superalgebra that allows for an invariant bilinear form, so a non-degenerate one, in fact. Then we have the affine vertex algebra. Then I want to fix a nilpotent element, F, and it turns out an even nilpotent element, F, that can always be extended to an SL2 triple. So this means it's there is a corresponding, I mean, as long as the nilpotent element is non-zero. And so that means one can identify it with an embedding of SL2 in the Lie algebra. And then one wants to use this embedding to carefully define a differential that generalizes this one. In the SL2 case, it's a very simple thing. For higher rank, it will look more complicated. But the upshot will be we will, as a homology corresponding to a nilpotent part of the Lie algebra against some character, so this one you should interpret as a character on the nilpotent subalgebra, you will associate a W algebra, a new vertex algebra. And all of a sudden this gives us a huge family of new vertex algebras. Right? Now, so far we had vertex algebras associated to Lie algebras together with choices of levels, complex numbers. And now we will get vertex algebras associated to a Lie algebra together with a choice of level, a complex number, together with a choice of a nilpotent element. Right? And so, for example, of course, if so for example, it turns out inequivalent nilpotent elements of SLN are classified by partitions of the number n, and you can see that because if you write down your big SLN matrix, what can you do? You can just you choose your favorite partition of the integer n, and corresponding to this partition, you write down diagonal blocks of those sizes, for example, like this. And in each such block, you do the principal embedding of your nilpotent element, the regular embedding, so meaning the corresponding nilpotent orbit has full rank. And so there's, and you know, partitions of an integer n, that's already quite some number. Anyway, that's the motivation. And this is how you define W algebras, and then later I will tell you how W algebras are related to a different construction of new VOAs called coset construction. And I will also shortly mention another construction via screenings, but I only will mention that fairly shortly. So our setup is the following. We have in G Lie superalgebra together with a bilinear form.
You were writing as decrease in size since the previous stage. Basically, everything on that board is invisible, and this one will have a similar.
Even if you look upstairs? Well, anyway, I will be bigger. So then, what else do we have? We have our level. This is the K, and then to this data we have we associate the affine vertex algebra of G at level K, defined by this bilinear form. We had this before, and now we choose an element F in the Lie algebra, and F, what do we want it to be? We want it to be even and nilpotent. So there's a theorem called Jacobson-Morozov theorem that tells us this is equivalent, this is this theorem says that any such nilpotent element can be completed to an SL2 triple. And so what you in practice, of course, do is you not only choose a nilpotent element, but you immediately choose the corresponding SL2 triple. And you will use the whole triple for the definition. So this means we choose not only an F in G, but the F in G also defines us an E and an H in G. So that E, F, and H together give us an embedding of the Lie algebra SL2 in G. Here the nilpotent element I choose to be non-zero. Okay, and then one just normalizes differently than I used before. So let us just set X to be 1/2 H. Okay, and now we introduce a little bit of notation. So what do we have here? We have an SL2 subalgebra of G. G is a Lie superalgebra. Of course, I mean a finite dimensional one. So this means in particular G is a finite dimensional module for SL2. So it's a sum of finite dimensional irreducible representations, and in particular X semi-simply. So it's graded by X eigenvalue. And this normalization means it is half integer graded. And just notice that this K is not a good notation. So here, this Gn is the subspace, the eigenspace of eigenvalue n under the action of X.
The font is getting smaller.
I'm sorry. Yeah. Thanks for reminding me. Okay. Now we fix a basis Sn of each eigenspace, so that the union of these bases is a basis of G. And now we introduce a structure constants. We need to have some quite explicit formulas. Structure constants F alpha beta gamma, just by we take two basis vectors, we denote them Q alpha and Q beta. So this, and then we can expand it in terms of our basis, and the expansion coefficients are called structure constants. Okay. Now, what else do? We have a, just let's, so I need a lot of notation to start.
Is Q alpha somehow saying, is that the basis of this?
Yeah, so what we do is, so we have here, I mean our basis is Q alpha in S. We denote the basis vectors by Q alpha. So then we introduce the positive part and the negative part of the Lie algebra. And this positive part is exactly the positive part on which we want to do our gauge fixings. So we want to write down a differential that involves, is in particular the elements, the fields in here. And correspondingly, we denote S plus and minus the restriction of the basis to G plus and G minus. So now, now I will introduce two vertex algebras. So first of all, F of G plus is the free field vertex algebra associated to the vector space G plus its dual. And note that its dual you can naturally identify with G minus, because it's an invariant bilinear form, it's non-degenerate, and so this means every element in G plus has a non-trivial pairing with an element in G minus. Now, what did I tell you at some point now already 3 days ago, and you might have forgotten it? I gave a list of a bunch of vertex algebras one can associate to vector spaces with a bilinear form on it. And so this is our bilinear form on our Lie superalgebra, because it respects the grading, induces a non-degenerate bilinear form on G plus G minus. G plus and G is a Lie superalgebra, so this is a vector superspace, and we have an associated free field algebra. And this one we call F of G plus. So if we go back to the example of SL2, and the example of SL2, G plus would just be the one-dimensional subspace generated by E, G minus the one-dimensional subspace generated by F. The pairing, the OPE of E and F, the pairing of E and F is 1. And so that now you introduce one free fermion associated to E. Here we call it B. One free fermion associated to C. Associated to F. And the OPE of these free fermions is exactly given by the pairing of E and F. The pairing of E and F is 1. And this is here. So here, what does this mean? It means we introduce here fields. And phi sub alpha and with a sub-index, and we put the alpha at the bottom or top, depending on whether we want to think about it in being in G plus or G plus dual. So associated to a basis vector Q alpha.
Thomas?
Yeah.
Well, I don't understand why these are fermions with B. I mean, isn't E and F even?
Yeah. Remember the free. I introduced a free field algebra X associated to a vector superspace, where the field associated to an even element was always an odd field and vice versa. So the parity was reversed. So we had the free field algebra, where the free fields had a first order pole. The field associated to an even vector in the vector space was always odd, and the field associated to an odd element was always even. The parity there is always reversed. So it's good that you point that out. Okay, we have here, so we have this fields phi alpha, and I actually wanted exactly to point this out now. So we have that this field phi alpha is even, respectively odd, if the corresponding basis vector Q alpha is of opposite parity, is odd, respectively even.
Can you remind me, again, the free field vertex algebra, it's associated to what data?
Yeah, let me first write down the OPE. So, and the OPE of two such fields is 0 unless alpha is equal to beta, right? And here this one is a field corresponding to an element in the dual of G plus. This corresponds to an element in G plus, and this is the OPE. And can you please repeat your question?
To what data is a free field vertex algebra?
Yeah, so a free field vertex algebra is associated to a vector superspace together with a bilinear form. So what you then do is, so you have, in general, you have a vector superspace together with a bilinear form. And then you have an assignment to every vector in V. You have a corresponding field. Let's call it phi of V. And then phi of V has opposite parity as the corresponding vector in V. So exactly what I denote here. And the OPE of two such, the fields corresponding to two vectors, V and V prime, is just given by the pairing of V and V prime with a first order pole.
Is this formula supposed to determine the thing, or?
Yeah, it determines the thing. Yeah. I mean, this formula it determines the commutation relation, so it's equivalent to the modes of these fields. So if I write this in terms of modes, let me write now the vectors in upper index so that I have space for the mode index. So it means that the commutator of these ones is just this. Okay, no n here.
For example, how do you learn what is this thing applied to the vacuum?
How do you?
Z is supposed to be something which you apply to the vector. You get something.
Yeah, and you do the standard construction. Or on the vacuum, positive modes act as 0, negative 3.
What is positive?
This index.
Oh, I see.
Right? So it's really very, very similar to the whole affine VOA construction.
So the field has priority opposite to the vector. Is that convention, or should that follow from something you've written down? Like, is that forced?
Well, that's the finish. That's just how I introduced that. It's the only way a free field algebra where the OPEs of this form can possibly work, right? Because what is this? The bilinear form. You want it to be super symmetric, so you want it to be symmetric on the even part. Right? So this means, and assume that these two are even. So that what happens if I interchange the order of the two? I interchange the order of W and Z, which gives a minus sign. So that can only work out if it's odd, right? We will see it in a moment that we can also reverse parity, but that's more tricky. But it will be the next thing I'll do. And anyway, so please compare this simply to the SL2 example. Right? So here, and here I said B was my phi E. I hope I get upper and lower index correct, and the C, the phi E with an index on the other side. Okay, now we need one more free field algebra in order to define the complex. And this one more free field algebra is the reason for it is hidden in the 1/2. We want to define a character that fixes everything in the positive half and G plus to act as 0, except we want the E of the SL2 triple to act as 1. And but here we see if G1/2 is non-trivial, we will have a problem because the E can appear in the commutator. So, and in order to account for that, we have to introduce one more free field algebra, which only depends on this G1/2. In particular, if you look at the literature, roughly at 50% of the W algebras, this G1/2 vanishes. So then this whole problem doesn't appear. And in particular, in those W algebras that are historically studied, it doesn't appear. But somebody of you told me he or she is interested in superconformal algebras. Who was it? And anyway, and in that case, for example, this G1/2 is very, very important. Okay, anyway, so we have our F of SL2 has SL2 weight -1. So what does it mean? It means we can use F to introduce a pairing. Now I will denote it by these types of bracket on G1/2, just on the SL2 weight 1/2 subspace. Right? Because what can I do is I can take two vectors in there, A and B, and now what can I do is I can take the commutator of A and B. The commutator of A and B is something of weight 1. So this means if I pair this, and here this is the ordinary pairing, if I pair this with F, this has the chance to be non-zero. But now let's think about it. If A and B are both even, then the commutator is antisymmetric. So this means it defines me an antisymmetric bilinear form. And so this means, in contrast to here, where we have here on our G plus a supersymmetric bilinear form. It's the bilinear form. Yes, this is the bilinear form. Okay, and now we denote by F the free field algebra.
Is it actually possible for A and B to be even? There's no like spin statistics or something?
Yes, that happens. Right. So of course, you know, the bilinear form is consistent, so F is even, so it can only pair with something even. So this means this bilinear form is also consistent because this commutator is even if and only if A and B have the same parity, right? And now in the old string theory literature in particular, one was interested in particular in superconformal field theories, and in these superconformal field theories one wanted always to have correct spin statistics. That means bosonic fields being integer graded, having integer spin, and fermionic ones half integer spin, and in particular that requires that this G1/2 is purely odd in those cases. Right? This is not assumed here, and there are many cases for which this doesn't hold. So you get many W algebras that in that language are of false statistics.
Sorry, Thomas, if I look at the purely even case, that formula there is the Poisson bracket of G star, basically, right? I mean, if I identify G with the dual with the...
Yeah, and
this is used
yes, there is a notion of classical W algebras, and what you can do. Why don't I say that in private at some point? Sure. But yeah, there is a very nice relation between vertex algebras and Poisson vertex algebras that arise as classical limits, and what you point out is exactly happening in the classical limit. There was one more question, wasn't there? Okay. Good. Anyway. So this is a free field algebra and of reverse parity in the following sense. We have the generating fields are called phi alpha, maybe known as a different phi. Alpha is here now over a basis of G1/2, and the OPE of two such fields is given by this bilinear form. The pairing of the corresponding basis vectors with the first order pole. And the important thing to note is that this field phi alpha has the same parity as the corresponding basis vector. So really this is the free field algebra on the vector space G1/2 with reversed parity. So okay. Good. Now having this, the complex is the affine vertex algebra times these two free field algebras. So we denote here the C of, and now what does it depend on? It depends on these three parameters, and it's our affine vertex algebra at level K times the free field algebras. Okay, and what's the differential? It has a...
I'm confused about something.
Yes?
FG plus is somehow, there's just a notational confusion. FG plus and FG1/2 mean different things.
Can you say it again?
Do FG plus and G1/2, they're like different?
Yes, they are very different. I mean, FG plus is the free field algebra associated to the vector superspace. I could also write G plus G plus dual together with the bilinear form.
Maybe it's better so it doesn't.
Sure. It's just if I write down all these lengthy expression all the time, then it's just long. But the probably.
But it's very confusing if F means something different for FG plus and FG1/2.
Sure. So it's the free field.
It doesn't.
Right. I mean.
That's what it means. It means that somehow, there's this weird.
So FG plus. Absolutely, it would be better to write. I mean. It's the free field algebra associated to this this vector superspace with the obvious bilinear form, and FG1/2. The full notation that would make it good would be the free field algebra associated to the vector superspace G1/2 with reverse parity. I would maybe add the pi for parity reversal together with the bilinear form that I defined. Okay? But I don't want to write this all the time. Yes?
In the OP for capital phi, we have lower indices on the left-hand side and upper indices on the right-hand side. Is that a problem?
That's just notation. Yeah. Yeah. It's. That's just notation, and then you'll see. Let me write down the differential. It's all just for symmetry of the formulas. Well, okay, maybe it doesn't have any meaning at all. Okay, so what do we want to do now? We want to.
Excuse me?
Yes.
I think the G1 is same parity of basis and field, I think.
Yes, right.
Why-
Well, yeah, no, the fields have the same parity as the vectors. That means it's the parity reverse free field algebra. Because the free field algebra to a vector space, the fields always have reverse parity, so you reverse of the reverse. So the notation is correct, but I understand that this is confusing. Okay. Let me write it down and then add notation wherever you want me to. So the differential, and please compare it to the SL2 case. So we get one term here, so x alpha denotes the field corresponding to the basis vector q alpha, right? And so this is the term that on the left-hand side is the b times e. Then here we get here a term that is the sum over triples of elements in the positive part. We get again a sign for the parity of elements.
Is X alpha what was called Q alpha before?
X alpha is the shorthand notation for the field corresponding to the basis vector q alpha. So here you get a cubic term in the free fields, one with lower index, two with upper indices. And in fact, these two terms are what is called the standard Lie algebra differential for the nilpotent subalgebra G+. And then the next two terms are then the ones that correspond to the character. If I only had this one, you would do some kind of gauge fixing where you set the whole nilpotent half to 0. You can do this, you can get a vertex algebra. This vertex algebra is very boring.
Is S plus the sum of Sn for n positive, or the union of Sn for n positive?
Yeah, exactly. So S plus is the union of the Sn and the positive part of the basis. Okay, and here you get now your character. This is just given by the pairing with a nilpotent element f. And this expression is the reason why you denote the whole thing by f and not by e, just because the f appears explicit in the formula. And then you have a last term, which is also part of the character, which is only relevant if this half G1 half subspace is non-trivial. And then you get also here a pairing between a ghost, a fermion, and corresponding to G plus, and a free field corresponding to G1 half. Anyway, so okay. Now,
Can you put some parentheses?
yes, I can.
Maybe there should be beta in the last phase.
Yeah, you're right. I'll put the alpha here. So here we have. Here, this is one expression here, one here. Okay, so the differential has 4 terms. It naturally splits into 2 and 2.
And differential lives where? It's an element of what?
this differential. So this differential. Well, this is in the first place. If you look at this, if this one is even, this one is odd, and vice versa. So this term is always odd. Same thing happens here. This one is any non-zero term here is odd, and so every term here is odd, and this is just a field in this vertex algebra C.
So that tensor product of vertex.
That's the tensor product of vertex algebras. So this is a field in this vertex algebra, and now
Tensor product of vertex algebras is not something you promise that always exists either.
now this is the
Exists or
no. The tensor product on the representation category of vertex algebras does not always exist, but this is just the tensor product of vertex algebras, so the underlying vertex. I of course have not defined it, but for the same problem as many things in this lecture, right? So that, let me just say it in words. The tensor product of two vertex algebra is the vertex algebra whose underlying vector space is the tensor product of the underlying vector spaces, and whose fields are the natural ones. Okay,
why is it that you should write normal ordering between?
There's no necessity for that. It's the only so normal ordering is only necessary here. Right. In all other places it's irrelevant.
In our example, we have only two terms.
Yeah, right, because we only have two terms, because S1/2 vanishes, it's 0, so that's why this one vanishes. And this one here is given by the Lie algebra structure on the positive part, but in our case the positive part is just the one-dimensional Lie algebra generated by E, it's commutative, and so this term here vanishes because the positive part is commutative. So this means in the SL2 case we only this term is non-zero and the character is non-zero. And this character, of course, collapses quite a bit because F and E have pairing 1, and then this whole sum is just the field phi alpha, which is the field. And now we see that I should have written it this way.
Is this thing dependent on all these choices you made of basis, or is it in fact independent of this thing?
This thing.
When you write C, G, K, F.
Yes. Right. So the field D depends on the choice. So if you want, I could also add a label for the choice of the basis. So, but the homology doesn't depend on any choice. So the theorem is. So you carefully look. I mean, the reason for defining it this way is because it satisfies this property. So and what is very well known is that without this character, you already get. So already this first part has this property, and you know that you want to do a kind of a fixing of this type. So you add it, and then you do the computation, and because E itself is in the derived subalgebra if G1/2 is non-trivial, you have to add one correction to it to get this property. Anyway, so what does this mean? In particular, the zero mode of this field D0 has the property that it squares to 0, and now I can define the W algebra of the affine vertex algebra of G at level K, corresponding to the nilpotent element F, is defined as the homology of this complex. Right, so now I get a complex. Did I? K and F. For this differential D0. Okay, and it turns out it doesn't depend on choices like the basis. It's always the same thing. And that's the definition.
What was the point of writing this whole big field if you only ever wanted D0? What was the point of writing this whole field if you only ever wanted D0?
Because writing the D0 explicitly would have been even longer.
Is there some general fact that says if you have some field with
Absolutely, that always, yeah. So it's right. It's an exercise to show this consequence, and it follows from.
No, not that question. I was asking if you have any vertex, there's any field with this property.
Yeah.
Is it true that the homology is again vertex?
Yes, that's always true. Yeah.
And you need this whole business that it came from this field with commutator with itself zero.
So you surely can relax this, but if you have it in this setup, then it implies this. So yeah, if you just take an arbitrary odd operator with this property, you don't have it under guarantee. So
if G was just an ordinary Lie algebra, this thing will have an odd part.
Yeah, it has an odd part because, right, if this is an ordinary Lie algebra, then this is purely odd.
Okay, but somehow it's not killed by D0. Something survives. That's my question.
I will state this, the structural theorem in a moment. Right? Now, of course, we want to know what is this, this homology. So, yeah, any questions? Yeah?
I think I missed, but you said that the first two terms in DC are gauge fixing terms. Gauge fixing terms.
No. It's the first. So let's just do this. We write a D to be D1 plus D2 plus D3 plus D4, and exactly in this order. And then it turns out the first two terms, they are what is usually called the standard semi-infinite Lie algebra cohomology differential. I mean, the zero mode is the standard semi-infinite Lie algebra cohomology differential for this G+, for this nilpotent subalgebra. Something that is you simply already study in Lie theory quite a bit. And then the D3 and D4, you could say this is just denoted by chi for a character. The zero mode of this one is already a differential. It already squares to 0. And so that means the cohomology is also a vertex algebra. It turns out this vertex algebra is small and boring. So for, yeah.
Can you expand on the thing which you said that somehow this semi-infinite whatever is some version of Chatelet-Eilenberg complex?
Yeah.
And so it's a statement that this is like some kind of. Maybe I'll just ask you later.
Yeah, why don't you please ask me later? So, the point is, it is something that is not only motivated from physics, but also from Lie theory. But it only becomes interesting because of adding this character. And so for example, if you take an affine vertex algebra and you take a principal nilpotent element, then it turns out if you take the cohomology without character, you would just get the Heisenberg algebra associated to the Cartan subalgebra. That's not. I mean, we don't want to do some very fancy setup to recover something we already know, right? That's definitely not. Anyway, it's time for a break. I have given you the definition. You see it's quite technical. Next thing is I will state the main structural theorem. And it's, in fact, a really nice exercise to prove it. I won't do that. And then I will tell you that there's a completely different construction of vertex algebras called coset construction. And if you look very, very carefully, then you see relations between the two, which is quite exciting. And in fact, it is predicted by physics, important for physics. It's important for all these other applications as well, to which I hopefully come this afternoon. Let's have a coffee.